Hey everyone, welcome! Have you ever stopped to think about how some things in life seem to move together, while others work like total opposites? Well, in this explainer, we're going to dive into that with a super powerful math tool, direct and inverse proportions. It might sound a little fancy, but trust me, by the end you'll see how it explains everything from cooking dinner to how long it takes to get somewhere.
Okay, so let's kick things off with a situation you've probably seen right in your own kitchen. Gopi is making rice. The recipe is perfect for 2 people, but what happens when guests show up? He's got to make more rice, which means, he's going to need more water. But how much more exactly? Getting that ratio just right is precisely what proportions are all about. And you know, this kind of relationship is literally everywhere you look. Think about it. More rice, you need more water. If a school gets more students, well, they've got to make more midday meals, right? And if you buy fewer items at the store, your bill goes down. It's a chain reaction. One thing changes, and it pulls another thing along with it.
All right, you ready to dive in? Here's what we've got on the agenda today. We're going to start with direct proportion. That's when things move in the same direction. Then we'll flip it and look at its opposite, inverse proportion. We'll put them head to head, and then we'll even level up with something called compound proportions. And to wrap it all up, I'll give you some of my best tips to help you ace your exams.
All right, first up, direct proportion. This is basically when 2 things are moving in sync, kind of like dance partners. When one increases, the other increases. When one decreases, the other one does too. So, here's the deal. For something to be a real direct proportion, there's a special rule. The ratio between the 2 things has to stay the same, always. It's not enough for them just to go up together. If you double the amount of rice, you have to exactly double the amount of water. That constant, unchanging ratio is the absolute key.
And this little formula right here, this is our secret weapon for solving these kinds of problems. X divided by y is always equal to k, which we call the constant. This means if we have 2 different situations, the ratio from the first one is going to be exactly equal to the ratio from the second one. Let's see it in action.
Okay, let's put this into practice. We're going to walk through a classic textbook problem together, step by step. It makes sense that if you buy more tea packets, it's going to cost more, right? So this definitely sounds like a job for direct proportion. Okay, the very first thing you should always do is get organized. Making a table like this is a game changer, trust me. It makes everything super clear. We've got case 1, 65 packets for 2,600 rupees, and case 2, we're trying to find the cost, our Y2, for 75 packets. See, now that everything's laid out, the next part is easy. We just pop these numbers into our formula. The ratio of packets to cost in the first case has to be equal to the ratio in the second case. So, 65 over 2,600 equals 75 over our mystery cost.
And now for the fun part. We just solve for that question mark. A little bit of math later, and voila, we find out that Y2 is $3,000. So, 75 packets will cost $3,000. Not too bad, right? The key is just setting it up correctly.
Okay, but hold on a sec. I gotta warn you about a really common trap. Just because 2 things are increasing together, it doesn't automatically mean it's a direct proportion. Check out these parking charges. The time goes from 4 hours to 8 hours, it doubles. But the cost? It doesn't double. Since that ratio isn't constant, this is not a direct proportion. You've always got to check the math.
All right, so we've got the hang of things moving together. But what happens when they move in opposite directions? Let's check out our next tool, inverse proportion. I like to call this the seesaw effect.
The seesaw is literally the perfect way to picture this. As one side goes up, the other side has to go down. And here's the big difference to remember. With inverse proportion, it's not the ratio that stays constant, it's the product of the 2 things, what you get when you multiply them.
And that idea gives us our magic formula for inverse proportion. X times y is always the same number, our constant k. So the product from our first scenario will always equal the product from our second.
Let's look at a classic example you'll definitely see, speed and time. Think about it. If you drive faster, what happens to the time it takes to get somewhere? It's got to go down, right? That's the seesaw in action.
And what's our first step? You guessed it, we organize everything in a neat little table. We've got our speed and time for case 1, and we want to find the new time for case 2 when we've sped up to 80 kilometers per hour. Okay, so this time we're using our inverse proportion formula. We set the products equal. So 60 kilometers per hour times 4 hours has to equal 80 kilometers per hour times our new unknown time, y2. We do the math,
And we find that the new time is just 3 hours. And that totally makes sense, right? We drove faster, so we got there quicker.
Okay, we've met both our contenders. Now it's time for the showdown. Direct versus inverse. Let's put them head to head so you'll never get them mixed up.
This little chart here sums it all up beautifully. For direct, everything moves together, and the ratio, x divided by y, is constant. For inverse, they move in opposite directions, and the product, x times y, is constant. And if you ever forget, just think about a road trip. More distance means you use more gas, that's direct, but more speed means it takes you less time, that's inverse.
All right, are you ready to level up? So far, we've only dealt with two things changing. But what happens when one thing depends on two or more other things changing at the same time? Well, that's where compound proportions come in.
Whoa, look at this problem. The total cost depends on two different things: how many students there are and for how many days. The trick here is to just break it down into smaller pieces. You'd figure out the relationship between cost and students. That's direct. Then you'd figure out the relationship between cost and days, also direct. Then you just combine those two relationships to get the final answer. We're not going to solve the whole thing right now, but that's the big idea. Turn a complicated problem into simple parts you already know how to do.
Okay, you've absorbed a lot of theory. Now it's time to put it into practice and get you totally prepped for your exams.
All right, here's one for you to try. So a truck travels 14 kilometers in 25 minutes. How far can it go in 5 hours? First question to ask yourself, is this direct or inverse? More time should mean more distance, right? So go ahead and pause the explainer, give it a shot, and come back when you think you've got it. Oh, and a little hint, watch your units.
Okay, let's do a quick recap of the two most important formulas you need to know. For direct proportion, it's all about equal ratios. For inverse proportion, it's all about equal products. You gotta burn these into your brain.
And before we go, here are my top 3 tips to help you crush any proportion question on your exam. Number 1, read the question super carefully to figure out if it's direct or inverse. Number 2, always, and I mean always, make a table. It seriously helps you avoid silly mistakes. And number 3, do a quick sanity check at the end. Does your answer actually make sense in the real world? Like, more workers should take less time, right? If your answer says more, you might have made a mistake.
And that's all for today. You know, the big idea here is that proportion isn't just some random chapter in your math book. It's a lens for seeing how the world works in a predictable way. You now have the tools to calculate these relationships everywhere. In our next lesson, we're going to tackle some more exam-type problems to really build up your confidence. I'll see you then.
Hello, students. Have you ever looked at a big construction project and wondered how they figure out exactly how many workers they need to finish on time? It's not just a lucky guess, you know? It's all about math. Today, we're going to dive into the tool they use, called compound proportion. Now, I know it might sound a little complicated, but I promise, by the end of this, you'll see just how logical and useful it really is. Let's get started. Okay, let's kick things off with a classic problem like this one. We've got workers, we've got the size of a wall, and we've got a deadline in days. Now, if we only had workers in days, we could use simple inverse proportion. And if we only had workers in the wall size, we'd use direct proportion. But since all three things are changing at once, all those simple methods just aren't going to work. We need something a bit more powerful.
So, yeah, what do you do in a situation like this, with so many moving parts? We need a way to combine, or compound, all these different relationships into one single solvable problem.
And that's exactly where compound proportion comes in. So let's get a really clear idea of what this is and why it's such a great tool for solving these more complex real-world problems.
Basically, you use compound proportion whenever the one thing you're trying to figure out is affected by a bunch of other things that are all changing at the same time. Remember that wall problem? The number of workers you need depends on both the length of the wall and the number of days you have.
Here's another way to think about it that might hit closer to home. Imagine you're baking cookies. If you invite more guests, you'll need more flour, right? That's one direct relationship. But what if you also decide to make each cookie bigger? Well, then you'll need even more flour. That's a second direct relationship. To get the right amount of flour, you have to consider both things together. You have to compound them. So the very first thing we have to do when we see one of these problems is figure out the relationships between our quantities. As you can see here, they can be all direct, where everything goes up together, like more students for more days means a higher cost. They can be all inverse, where increasing two things makes the third one go down, like if you work more hours per day for more days, you'll need fewer workers. Or, and this is pretty common, they can be mixed, like in that painting example we'll look at in just a minute. Now for the good news. You don't have to just guess your way through these things. There's a reliable step-by-step method that works every single time. If you can learn these steps, you'll never feel lost. So let's walk through the process together. This 4-step method is basically our roadmap. First, we put all the data in a table to get organized. Second, and this is super important, we figure out the relationships between our unknown value and everything else. Third, we turn those relationships into ratios, and you can see that little reminder there. It is absolutely critical to remember to invert the ratio for any inverse proportions. And finally, we just set up our equation and solve. See? It turns a complicated word problem into a simple checklist. Okay, time to put our new method into practice. We'll start off with an example where all the relationships are direct, just to get the hang of it. All right, here's our first problem. We know the cost for 35 students over 24 days. The question is, what's the cost for a different number of students and for a different number of days? So the thing we're trying to find, our x, is the final charge in rupees. So, following our method, the very first step is to get organized. We just make a simple table. The first row, which we'll call case 1, has all the info we were given, 35 students, 24 days, and the charge we know. The second row, case 2, is for the situation we're solving for, 25 students, 18 days, and the unknown charge, which we'll just label x. Now for step 2, figuring out the relationships. We always compare our unknown quantity, in this case charges, to each of the others one by one. So first, let's look at charges versus students. Just ask yourself, if the number of days stayed the same, would more students cost more or less? Well, more, of course, so that's a direct proportion. Now let's do charges versus days. If the number of students stayed the same, would more days in the mess cost more or less? Again, it's more, so that's another direct proportion. Great. Now we can combine steps 3 and 4 to build our equation. The ratio of the charges, which is 3,300 to x, is going to be equal to the product of the other two ratios. So we write the ratio of students as 35 to 25, and the ratio of days as 24 to 18. And since both relationships were direct, we don't need to flip or invert anything. From here, you just solve for x. Excellent. Now that we've seen how a direct case works, let's try a more common and maybe slightly trickier example. This is a mixed case with both direct and inverse relationships. In this problem, the unknown that we need to find is the number of painters, and the other things that are changing are the length of the wall and the number of days they have to get the job done. Okay, once again, we start with step 1. We put everything in a table. I know it seems simple, but this step really helps us see all the numbers from the word problem laid out clearly. It separates what we already know in case 1 from what we need to find in case 2. Now for step 2, identifying the relationships. First up, painters versus wall length. If the wall is longer, are you going to need more painters or fewer? More, right? So that's a direct relationship. But now let's look at painters versus days. If you have more days to finish the same job, can you get it done with fewer painters? Yes, you can. This is an inverse relationship. And spotting this difference is absolutely key. And this brings us to the most critical part of the entire method, which happens in step 3. When we build our equation, we start with the ratio of painters, 6 to x. For the direct relationship with the wall length, the ratio stays just as it is, 96 to 72. But for the inverse relationship with the days, we have to invert the ratio. So instead of writing 8 to 3, we flip it to become 3 to 8. This flip is how we mathematically account for that inverse relationship. Getting this one step right is the secret to solving the whole problem correctly. Speaking of getting it right, let's really quickly go over some common mistakes so you can be sure to avoid them on your tests. These are the 4 big traps to watch out for. A lot of students rush past the identification step, or they get direct and inverse mixed up, or they just make simple calculation errors. But the single biggest mistake, the one highlighted on the slide, is forgetting to flip the ratio for an inverse proportion. Always, always pause and ask yourself, is this direct or is this inverse before you write down that ratio? All right, now it's your turn to do a little thinking. I'm going to put a question up on the screen for you. Take a look at this problem. You can go ahead and pause here to think it through. First, notice how many quantities are changing. It's just men and days. So do you even need the compound proportion method here? And second, what's the relationship between the number of men and the number of days it takes to do a job? Is it direct or inverse? If you said this is a simple inverse proportion, you are absolutely correct. With fewer men, it's going to take more days. You don't need the whole compound method for this one. Well done.
Great work today, everyone. Let's just quickly summarize the most important points that you need to take away for your exams. If you just remember these key points, you'll be in fantastic shape. Build your table, identify the relationships, and please, I'll say it one more time, remember to invert the ratio for any inverse relationship. And finally, just give your answer a quick common sense check. Does the number you got seem reasonable? So here's the number one takeaway for your exams. When you're reading a word problem and you see 3 or more different things changing at once, workers, days, hours, length, whatever it is, a little alarm bell should go off in your head that says, aha, this is a job for the compound proportion method. Keep practicing these steps. You'll find that the more you use this method, the easier and more natural it becomes. Next time we meet, we'll use this same framework to solve some even more challenging exam-style questions together. Thanks for joining this explainer.
Please do like, share and subscribe my YouTube channel.